Hey everyone, today we are competing in Codeforces round 729, which is starting in just a couple of seconds. Pretty fast A. I do not know if this is correct. Oh. Alright, I'm gonna submit this. Why does this still have me on Kotlin? Unexpected error? Okay, let's try that again. Alright. Hope this is correct. I'm not certain that it is. Actually, I think this is probably right. I don't know. Okay, I think this makes sense. But let's see. Never mind, it's not. Oh, wait, hold on a sec. Okay, why am I getting 8 for 2? Oh, I'm stupid. 2, 5, 7, 10, 26, yeah. Alright, cool. Oh wait, shoot, I submitted as Kotlin. TLE on B? Oh, I have TLE when A equals 1, must be. Okay. That's unfortunate, I should have thought that case. Yeah, there we go. Cool. Wait, hold on. Did my real submission? Okay, my real submission to C did not go through. It just got submitted in Kotlin. All right. That's unfortunate. Penalty is worse than I would like, but that's interesting. So let's see, we should count the contribution of each element individually. All right, that's good. Both of those passed pre-tests. And for that, I think we can, man, this is going to be kind of annoying to deal with. This would be much easier if the elements were all distinct. I mean, I guess we can just like say as adopt a convention that elements that appear first are lower than elements that appear later. All right, I think I'm gonna give this a go. What's the time limit on this? 3 seconds, perfect. Alrighty. I have very little confidence in this working, but we're about to see. Alright, well that should not be happening. Oh wait, no, never mind. That does make sense actually. I think. Oh, I see. There we go. Cool. Alright, I feel good about this. Famous last words. The fact that this problem is so simple, and yeah, it's an E, kind of scares me. I find myself very concerned here. Also, okay, so evidently they do not want us to write a solution that involves modular inversion. Okay, so it seems like it might be good to casework on the first element that is actually smaller, because afterwards we can kind of do whatever we want. Like, you know, we can maybe do DP on like the number of elements that have been placed and then the inversion count. Or then, the inversion gap, I guess. Is the appropriate term. But then how do we do transitions efficiently, I guess, is the question. I guess actually maybe we can compute one set of transitions and then yeah, I think this might work. Make sure my D passes. Yeah, cool. Alright. I think I kind of know how to do this, maybe? Okay, so first step is, what is the first step? much memory do I have? Okay, I can declare this array, I think. Is there a lower time limit on this one? That's annoying, actually. It's quite annoying. Is this still gonna be fast enough? I'm gonna say it will. I guess I can custom invocation it later if I'm worried. Do I need my compo library for this? I might. Actually, I'm actually gonna have to compute the choose functions manually. I don't need to do percent equals mod. It's the benefit of a mod in class. Alright, so Okay, why am I getting 0? Also, I'm pretty sure I'm declaring this array way too big. Yeah, I am. Save a lot of time that way. Oh. I'm stupid. Shouldn't be having this problem though, but I should not be getting 0 anyway. Oh. That would do it. Why is dp of 0 of cap being changed? Oh wait, why is ss of 0 of cap? Equal to 0? Doesn't make any sense. Oh. Oops. Alright, so now I'm overcounting somehow. Actually, here, let me, okay, I actually don't know if this is correct. wonder if I'm I think I might be breaking ties wrong. Why did that take so long? Okay, let's see. So this entry is wrong. Oh, I know what's going on here. I'm computing this DP incorrectly. Okay, how do I handle this correctly? So I actually am going to go ahead and compute my suffix sums up here. Kind of worried about about TLE on the easy subtask actually, which is like kind of annoying. In fact, maybe I'll just declare my array. Do I have room to declare my arrays on the stack? Wait, hold on, I don't have enough room for these arrays at all, do I? Shoot, okay, so do I need to like compute that? I guess I can compute the answers in place. Yeah, that's what I better do. It's unfortunate this is taking a lot longer than it realistically should. And I'm going to need to refactor all of this pretty much. Okay, that should not be happening. Alright, I guess we're like double subtracting somewhere. Let's see. Oh. Oh. Alright, well that took much longer than it should have. I'm going to make sure E1 passes before I submit E2. Let me check M2. Compilation error. Did I submit the wrong file or something? What the heck is going on here? Oh, I forgot to delete these 5 things. That would do it, I guess. Crap, okay. All right, let's see. I could write a stress tester, but it won't really let me get to particularly high values of M or of N. Maybe I should do it anyway. I feel like even just getting up to like n equals 6 could be helpful. What do you mean P2 wasn't declared in the scope? Oh, yeah. This line. Okay, so it's slightly off on n equals 6. This is going to be fun to debug. In fact, I don't really see any particularly nice way to get rid of this, or to handle this. I'm kind of curious. Let me try something. this is interesting. So for the 6 case, the only place where it's failing is when there are already 2 elements placed, which is weird because that seems like it should be pretty much identical to the 4 case. I didn't like screw up my choose function, did I? No, okay, the choose function is fine. Oh my god, I'm an idiot. The order matters. Oh my gosh. Wow, I can't believe I missed that. Okay. Is that correct? Yeah, that's right, and okay. I'm gonna give it a moment to run. just in case there's some weird edge case later on. Would have thought this would be much faster. Like if this is anywhere near TLEing, I'm gonna be pretty concerned. I'm also honestly pretty surprised there's so many pretests because there aren't that many values of n. Okay, 124 ms, that's fine. I'm actually surprised it's taking that long. I'm gonna... Oh, shoot. Alright, well, that's about 2 seconds on my machine. Might be a little borderline, but we'll see. They have to have had an n equals 500 case by this point, so like I feel like if it doesn't fail by test 18, there's no way it's going to TLE. Just wouldn't make any sense. And it doesn't really seem like it's testing any slower than my E1. I would assume there are going to be a few more tests though, because I would think that every pretest for E1 is also going to be a test for E2. Alright, cool. Well, that's the contest. Alright, well, let's see, are people able to overtake me? Yeah, it's possible. So it's funny, I've been through all that, and I actually still don't know how E1 is harder than, or is easier than E2. I guess maybe like you're able to compute the DP without this prefix sum optimization I use. Maybe that's it. It's weird because I actually don't think it's, because I don't really think E1 is easier by any non-trivial degree. Like I genuinely don't see how having the extra factor of n really helps you, because you need to come up with the same DP idea, and all it really saves you from doing is this just mildly annoying prefix sum stuff. Which, I mean, I guess then it makes, like, I think the 2000, 1000 score distribution makes a lot of sense. But I don't see why so many people are going for E1 before E2. Like, that part doesn't really make sense to me. Anyway, yeah, so... I don't know, I feel like I definitely could have won this if I had, I don't know, not done a few things less stupidly. Like, I mean, avoiding the WA or the TLE on B as well as the WA on E, both of which I think were very dumb errors. Alone, that would have been 100 points. And then, you know, you also factor in the fact that it would have saved me, much time did I spend debugging the WA? Yeah, 13 minutes. And so 13 minutes on a 3,000 point problem, I think that would be 156 points right there. So yeah, I mean, you factor all that in, and that definitely could have been a win if I was, I mean, in fact, like, the error up here with my choose function alone was the only thing that was stopping me from, or that was keeping me out of first place, so that's kind of unfortunate, but overall it was a pretty good contest. Can't be too unhappy. Finished the set, so that is nice. Yeah, I guess if people are curious, I can go over my solutions to the problems real quick. Probably not going to go into too much detail. But so for A, we're given a multi-set with 2n integers, and we want to determine if we can split the integers into n pairs such that the sum of the two elements in each pair is odd. And so the key idea for A is to realize that the sum of two elements in a pair is going to be odd if one of them is even and the other one is odd. And so that means that we basically need to pair up each even integer with an odd integer. And so there need to be the same number of even and odd integers. And that's pretty much all there is to it. So we just count up the integers. Here what I do is I create a CNT array for each parity, and then I increment the count of x mod 2. And then here you could do, I just print yes if there's n even integers, because if there are n even integers, then there have to be n odd integers. You could also do it like this: CNT of 0 equals CNT of 1, i.e. the number of even integers is the same as the number of odd integers. That would be the most directly equivalent to the condition that we're looking at. But yeah, overall pretty simple problem. We just need to test whether it's possible to pair up the even integers with the odd integers. Okay, problem B. We're generating a set by starting with 1, and then for all numbers x in the set, we're adding x times a and x plus b to the set. And we want to figure out whether an integer n is going to be in the set given a and b. So I actually think this is a really nice problem. The way I kind of figured this out is by writing the general form for what an element of the set is going to look like on paper. And so let me try and approximate what I did in my Scratch work. I started recording, right? Yeah, I started recording. That's good. Okay, so I'll kind of approximate what I wrote out on my Scratch work. But let's say that when we compute n, we use the multiplication by a operation k times. So that means that the initial 1 is going to turn into a to the k. But moreover, if for each b we add before we multiply by a even once, that those b's are also going to be multiplied by a to the k. So like, for example, we might have, so like let's say we add b twice, then we would have 1 plus 2b, and then after k multiplications by a, we would get 1 plus 2b times a to the k, or alternatively a to the k plus 2b a to the k. And so, and similarly, so if you multiply by a, let's say you multiply by a once, and then you add b, and then you multiply by a k minus 1 times, then you end up with a to the k plus ba to the k minus 1. And so if you continue in this manner, the idea is basically that we're always going to have 1 a to the k, and then we're going to have some number of, so like let's just say, I don't know, ck times ba to the k, plus where ck is the number of times we add b before we multiply by a even once, plus ck minus 1 times p times ba to the k minus 1, where ck minus 1 is the number of times we add b after the first multiplication by a, and then we multiply by a k minus 1 more times, and so on until we get down to c0 b a to the 0, which is just c0 b. And this step represents the number of times we add b after all k multiplications by a. And so then you realize that the set of numbers the set of numbers in the set is exactly the set of numbers of this form for some k. And so then the key observation is that all of these terms except a to the k are divisible by b. And in fact, so it's necessary, and so that means that in order for n to be expressible in this form, we're going to need n minus a to the k to be divisible by b for some k. And so that's a necessary condition that we get as a result of this form. We can also quickly see that it's a sufficient condition, because if n minus a to the k is divisible by b, so like let's say n equals a to the k plus mb, then we can generate n by multiplying by a k times and then adding b m times. So that means that if n minus a to the k is divisible by b, that's necessary, or for some k, that's necessary and sufficient for n to be an element of our set. Okay, so given that, what we're going to do is we just generate the powers of a, which I do using this cur variable. And then if n minus a power of a is equal to 0 mod b, then we print yes. If this is not the case for any such power, we print no. I got TLE initially because I didn't consider the the a equals 1 case, and that led to an infinite loop because here, as you can see, I keep generating powers of a while the current power of a is less than or equal to n, and that doesn't work if a equals 1, because then you just sort of get your powers of a are just going to be 1, 1, 1, 1, and they never go above n. So that case has to be handled separately. But other than that, the implementation is pretty simple once you sit down and do the math. Fun problem, I thought. Okay, so problem C, strange function. Let f of I denote the minimum positive integer x such that x is not a divisor of I. Compute the sum from 1 to n of f of I. All right. Oh, whoops. Okay. So here, the way I started by thinking about this is I thought, okay, so it's probably going to, so for problems like this, especially because n can be up to 10 to the 16, it's probably going to make more sense to look at the values of f of I and think about how many times each value occurs, rather than to think about the each of the possible values of I and to think about f of I for each value of I. So that's how I started thinking about this problem. And so I thought, okay, so when is f of I equal to 1? Well, 1 is always a divisor of I, so f of I can never equal 1. All right, so when is f of I equals 2? So this happens when when 2 is the minimum positive integer that is not a divisor of I. So for 2 to not be a divisor of I is going to have to be odd. And we don't have to worry about x being the minimum of such integer because 1 is never going to be a valid result. So 2 is the smallest possible answer. What about f of I equals 3? So first of all, in order for 3 to be the minimum positive integer, not a divisor of I, that means 2 has to be a divisor of I. So I has to be divisible by 2. But also 3 cannot be a divisor of I. And in particular, it'll be helpful to say that since we've already said that I has to be divisible by 2, we can say that it's equivalent, or saying that I cannot be divisible by 3 is equivalent to saying that I cannot be divisible by both 2 and 3. So that is, it can't be divisible by the LCM of 2 and 3, which is 6. So that means for the answer to be 3, or for f of I to be 3, I has to be divisible by 2, but not 6. Okay, and so what about 4? Here, I is going to, so 2 and 3 both have to be divisors of I, because otherwise 4 can't be the minimum positive integer that's not a divisor. So that means that I has to be divisible by both 2 and 3, and their LCM is 6. But then it can't be divisible by 4, and since it's divisible by 6, the next integer, since it's divisible by 6, that's equivalent to saying it can't be divisible by the LCM of 6 and 4, which is 12. And so it goes on like that for a while. Like for when f of I is 5, I has to be divisible by 12, so as not to make the answer 4 or less. But it can't be divisible by LCM of 12 and 5, which is 60. And so that's basically the pattern here. So with that, let me show my solution. So the first thing I did is I write an LCM helper function. I think C++ has something built in, but I wanted to write my own because since n is really big, I wanted to make extra sure that I was handling the case when the LCM is really large properly, so as to avoid long overflow. Looking back on it now, this was probably unnecessary because I think the values are never really going to get that big, because if you look, we're sort of taking the LCM of 1 through n for each n, and that's going to be greater than 10 to the 16 pretty quickly. If we just start multiplying together all the smallest primes, for example, 2 times 3 times 5 times 7 times 11 times 13, that's going to get to be really large really quickly. So I probably didn't need to do this, but here I'm just using the built-in GCD function, and then the fact that the LCM of A and B is equal to A times B divided by the GCD of A and B. That's just a good math fact to know in general. And then here what this line is doing is it's saying basically if in order to prevent long overflow, it's saying if A times B divided by G is greater than 10 to the 18, and I'm expressing that in logarithmic form. So if log 10a plus log 10b minus log 10g is greater than 18, then I'm just returning 10 to the 18 plus 1, and otherwise I'm computing and returning the LCM. And that's how I write an LCM function in a way that's safe from long overflow. Again, wasn't really necessary to do that, but I did it anyway. Okay, so not sure why I called these variables CG and NG, given there. I think I was going for current GCD and new GCD, but obviously they're LCM, so that was kind of silly. But then essentially what I'm doing here is I'm saying, okay, CG is the LCM of the numbers 1 through I minus 1, and NG is the number of integers. NG is the number, or is the LCM of 1 through I. And then the f of I is going to be I in general if I is divisible by, here, let me write this out formally. F of I equals k if I is divisible by LCM of 1, 2, up to k minus 1, but not LCM of 1, 2, k. And in order to count these values, the trick I use is to observe that anything divisible by this LCM is definitely going to be divisible by this LCM, because to be divisible by this, a number has to divide has to be divisible by 1, 2, and all the numbers up to k. So it's certainly going to be divisible by all the integers up to k minus 1. And so that means that what I can do is I can count the number of things divisible by this, and just subtract out the number of things divisible by this. And so this value in my code is CG, and this in my code is NG. So I just need to take the number of things divisible by CG and subtract the number of integers divisible by NG. And in order to compute the number of integers divisible by CG up to n, that's just n over CG. And likewise, the thing we subtract out is just n over NG. And so then I add so that cur stores the number of values whose f of x is I. And so then I add cur times I to the answer. As you can see, I looped for a while. The fact that my loop bound is so high, I'm pretty sure it would have worked even if I just had I going up to 100 or something. But the reason I did this was so that I didn't need to worry about actually computing when our LCM was going to get too big. Instead, I just say, okay, as soon as the LCM is greater than n, it's going to be we're not going to have any more divisors of that LCM, or any more multiples of that LCM, so we can just break. Okay, that felt a little hand-wavy, but if you have trouble following any of that, the editorial will explain it all in much more detail. Alright, so let's look at D. Okay, so this is a pretty interesting problem. So we have a sequence of operations we're performing, and each operation is either to add a certain element to a multiset, or just to delete the smallest element in the multiset. And we're going to take a subsequence of these operations, and we want to compute the sum of the elements in the multiset over all of the possible subsequences. So this again is an issue where this is very similar issue to problem C actually, in that if we were to consider all of the subsequences, that would be 2 to the n subsequences, which obviously is infeasible and is up to 500. No exponential time solution is going to work. So that means that it actually makes more sense here to go element by element. And it's for example, in the second test input, we would first count the number of, or the extent to which this first element contributes to the answer. And then we would count the number of times this element contributes to the answer, and so on and so forth. So the way I do that is by doing dp, and my dp state is so I do a two-dimensional dp for each R is basically the element that we're currently looking at, and so or element whose contribution we're currently counting. And so then the DP state is the number of operations we've seen so far, and that's this first dimension here. And the second dimension is the number of elements smaller than element R that are in our multiset right now. And this is important because whenever we hit a minus after we add element R to the multiset, we need to delete something smaller, because if we delete if at any point we delete element R from our answer or from our multiset, it's not going to contribute to the answer. Okay, so that's the DP setup. That turns out to be all the information we need to encode in our state. And then as far as the transitions, so there are a few special cases here. So the general idea is if we hit a dash, so I guess first of all, in any case, we can transition just by adding 1 to I and doing nothing to j, and that represents skipping an operation. But then the separate case is when we take an operation. And so if the operation is a deletion, then we're going to decrease j by 1. If there are any smaller elements in the array, we're going to delete one of them. And I guess if not, if j is already 0, then we aren't deleting any elements from the array. And that's what this line processes. This says like, okay, if j is greater than 0, then decrease j by 1. The one catch here is so that works when I is less than R, which that is when we haven't reached element R yet, so R isn't in the set. When I is greater than R, then we need j to be greater than 0 in order to take a deletion operation, because if j equals 0, then that means there are no elements smaller than element R in our multiset, and so we have to there are no elements smaller than element R, and so if we delete an operation, then element R would be removed. And since we want to count the number of subsequences that result in element R being in our set, removing R is no good. So that's why we have this separate case here. All right. So then the second case is, so otherwise in either of these two cases, our operation is a plus. And so here I'm saying, okay, if this element is smaller, or in order to avoid double counting, you need to have a way to break ties when you're deciding which element is smaller. So I say like either if the element is smaller or they're the same but it appears before element R. In that case, I'm saying I'm basically breaking ties by position here. Then we're adding a smaller element, and so we increase j by 1 when we transition here. And otherwise, we're adding the last case is when we're adding something larger than element R, and here that basically does nothing, because adding something larger than R isn't going to help us because we would always remove element R before we remove anything larger. The one case I handle up here separately is when I is equal to R, that is when we're processing element R, we have no choice but to just take element to R. And so we can't really do any of these transitions down here. All we have is just one transition that says, okay, take element to R. Okay, and so finally at the end, I add the value of element R multiplied by all of the possible numbers of ways there are to achieve element R, or to create a subsequence that will contain element R in the end. Okay. Problem E. This one is a lot of math that I think will be best explained in the editorial, so I'm not going to explain my solution to this in full detail. But I'll go ahead and give a general overview of the approach I'm taking. So the basic idea I'm using here is if P is lexicographically smaller than Q, then what that means is, let's say that P and Q will overlap for, let's say, m elements. So that means P sub 1 equals Q sub 1, P sub 2 equals Q sub 2, all the way up to P sub m equals Q sub m. But then P sub m plus 1 is less than Q sub m plus 1. And another important observation here is that if P and Q overlap for m elements, the exact values of these elements are irrelevant because they're going to contribute the same number of inversions to both permutations anyway. So they're not going to, which elements are chosen at this stage when both of these are the same is not going to affect whether the number of inversions in P will be larger than the number of inversions in Q. So my overall approach here is I'm iterating over the number of elements chose before like P and Q first diverge. So I'm iterating over this value of m, and then I'm iterating over P m plus 1 and Q m plus 1. So m P m plus 1 Q m plus 1. All right. So then the question is, okay, given all of this, given like the number of elements left and the first elements chosen for P and Q that diverge, the question is how many choices of the rest of the permutations will result in our two permutation, or P having more inversions than Q. That's what I was looking for. And so this essentially comes down to a DP. And again, this will be explained in much more detail in the editorial. But the idea is, I'm constructing the array of I'm constructing a permutation backward, or the permutations backwards, and I'm counting the number of ways to create each potential like difference in inversions. And so the idea is dp of cap is the number of cases where P has the same number of inversions as Q after a certain point. Cap plus 1 is the number of cases where P has one more inversion than Q after a certain point, and so on. And so the idea here is, if we think about an inversion as being, or if we think about like adding inversions as we append elements to the beginning of the array, the last element is going to have no inversion. The last element of a permutation is going to have no inversions or is never going to create an inversion because there are no elements later in the array for it to appear next to. And then the second to last element in the array could create one inversion if it's larger than the last element in the array, or no inversions if it's smaller. And so last element, no inversions. Second to last element, 0 inversions or 1 inversion. And similarly, the third to last element can create 0 to 2 inversions. And it creates 2 inversions if it's larger than both of the two elements that appear after it, 1 if it's in the middle, and 0 if it's the smallest, and so on. And so then the idea here is okay, so let's say we're adding the third to last element. That means we add 0 to 2 inversions to P, 0 to 2 inversions to Q. And so in total, we can compute that the inversion difference can change by, there's one way to add 2 inversions, and that's to add 2 inversions to P and none to Q. 2 ways to add 1 inversion, and that's if you add 2 to P and 1 to Q, or if you add 1 to P and 0 to Q. 3 ways to add 0 inversions, and that's if you just add 0, 1, or 2 to P and the same number to Q. And then 2 ways to add -1 inversions, if you add 1 to P and 2 to Q, or if you add 0 to P and 1 to Q. And then 1 way to add -2 inversions. And so you sort of can see a pattern here that continues throughout the possible inversion counts. And so then broadly what my code is doing is I'm computing this dp down here. And after you spot the pattern, you can compute it directly in n to the 4th time if you're doing the easy subtask. If you're doing the hard subtask, then you can optimize this using prefix, or I guess here I use suffix sums. And then up here, I compute the answer. Ways of n minus 1 minus I is basically counting the number of ways to place the first n minus 1 minus I elements. And then what I do is I iterate over I'm assuming that we place the largest n minus 1 minus I elements first, and so at the end we have elements 0, 0 up to I to place. And so then I'm iterating over which element j goes is equal to q m plus 1. And, or sorry, p m plus 1, and then q m plus 1 equals k. And then I count the ways to place the first n minus 1 minus I elements times this variable stores the number of permutations where in the remaining elements p is going to have at least k minus j plus 1 more inversions than q. So obviously this is an incomplete hand wavy explanation. I think it's going to be much easier to explain all the math via by like actually writing it out rather than just talking through it. And so that's why I'm waiting for. I would say I'll put a link to the editorial in the description if it's posted by the time I upload this. And I would encourage you to read that if you're curious about learning more about how all the math works. But hopefully this gives you a general idea of the overall solution path. All right, so I think that is about all. Oh, wow, someone found a hack. Let's see, this is obviously an alt. Okay, looks like some random gray got hacked on C. It's interesting, someone went straight to C. It's a little unfortunate in these div2s where they're hacking because the gray alts actually have a significant advantage over the reds because if you look here, they place everyone, so everyone who is out of competition is in a room with each other. And so here, like, if I were to try and find hacks, which I'm not going to because this is a div2 and that would be kind of boring, I would only be able to hack a bunch of gold and red people who, like, are pretty unlikely to do stupid janky things on the first few problems, whereas people in div2, or whereas I guess really the main problem is the alts. Like this guy's obviously an alt. People who are alting are able to hack a bunch of grays, which is unfortunate. People probably shouldn't alt in div2s. That's kind of silly. All right. Anyway, I think that is about all here. So yeah, thanks for watching.